We are an interesting species, an interesting mix. We are capable of such beautiful dreams and such horrible nightmares. You feel so lost and so cut off, so alone, only the fact that we are not alone. Because in all of our searching, the only thing we have found that makes this emptiness bearable is each other. Some wise words from Carl Sagan. A very, very good morning to all our senior dignitaries, faculty members, and students joining us from India, and warm greetings to all of those joining us from around the world. It gives me immense pleasure to receive you all towards our inaugural session for Introduction to Astrobiology, the online course that is being run by the Center of Excellence in Astrobiology at Amity University, Mumbai. We are honored to have with us visionaries who have closely followed the developments in astrobiology around the world and have fostered the establishment of our new center here in India. I am honored to introduce Dr. Aseem Chauhan. Dr. Chauhan is a founding trustee of the Amity Education Group and additional president of the Ritnan Balved Education Foundation. He is also the chairman of our Astrobiology Center, and he serves as the chancellor of several universities in India of Amity, in Rajasthan, Haryana, Mumbai, Uttar Pradesh, Chhattisgarh, and others. We also have with us Dr. Selvamurthy, sir, who is presently working in the capacity as a president of Amity Science, Technology, and Innovation Foundation. Dr. Selvamurthy has, he also serves as the Director General for Amity Directorate of Science and Innovation. He has served for 40 years at the Defense Research Development Organization here in India, and he retired as the Chief Controller R&D in Life Sciences and International Cooperation. I'm fondly led and given a lot of support by our Honorable Vice Chancellor, sir, Lieutenant General V.K. Sharma, who joins us from Gwalior, who's also the Vice Chancellor of Amity University, Madhya Pradesh. With these very words, I would like to welcome all of you to our course. And let me just show you a few slides before which we can quickly jump into our welcome notes from each of our leadership members, and we will introduce you to our chief guest for today as well. So very warm welcome to everybody here in India. I'm delighted to have you all with us. Now, this COVID time has brought around very unusual but also special circumstances. We have tried our level best here at Amity to ensure that we're able to reach out to students not just in India, but in fact around the world. We took it upon ourselves with a lot of support from our partners at NASA Astrobiology, Blue Marble Space Institute of Science, Mars Society Australia, Open University of UK. And we put together a small curriculum and converted that in the form of a series of webinars that will be running from this weekend all the way until the 25th of October. And the purpose here is to address the knowledge gap that exists in astrobiology research. Astrobiology being a new and upcoming field around the world, as well as here in India, there's not many education opportunities that exist for students outside of a few countries. And we have taken it upon ourselves to initiate the students from science and engineering and other disciplines into getting inspired and motivated and find some direction towards applying their fundamental knowledge and specializing in the field of astrobiology research. We were very fortunate to be promoted by several organizations around the world. And as a product of that, within 10 days of opening our registration, we were able to get about 795 participants sign up from 53 different countries, 6 different continents, and with a perfect mix of gender balance as well. We are very, very proud of achieving that. And there are people from all of these different countries, from different disciplines and education levels that ended up signing up for it. As soon as that happened, we realized the immense responsibility that has fallen upon our shoulders. And towards that, we wanted to ensure that these are just not lectures that we are delivering, but rather an engaging and interactive session by which we can actually measure the ability of the students to grasp these topics. And to do that, we came up with a course that was easy to handle for everybody and was engaging enough. And we had certain assessment tasks that were associated with it as well. We just put together a small infographic. This was a small exercise that the participants undertook even before the course started. So this is to show you how excited and motivated everybody was. We had our first orientation 2 weeks back, and we gave them a task that how would you call astrobiology the study of the origin, evolution, and distribution of life, how would you do that in your own language? And we had 36 languages, out of them 24 different languages of people. So just to show a diversity of who we are. I'm also very, very fortunate to receive the class instructors, some of those who are with us today online, Dr. Jennifer Blank, Dr. Aseem Khan, Dr. Michael Macy from UK, Dr. Alyssa from Harvard Law School, and of course our guest speaker, Dr. Jonathan Clark, who will be talking to us today. I will not go into further details. I think everybody has seen the timetable that we have. We have set ourselves for a very exciting course of journey in astrobiology, with topics covering from solar system, microbiology, the different missions and planets around us, and also a class on the human aspects of astrobiology. And there are several students who are with me today. So without further ado, I will now pass on the welcome note to our respected Vice Chancellor, sir, Lieutenant General V.K. Sharma. Sir, can we please have you? And if you could share with us a few notes of encouragement, sir.
Thank you very much, Dr. Siddharth Pandey. Dr. Aseem Chauhan ji, the President of Amity University, Mumbai, and the Additional President of RBEF, which is the mother funding body of all Amity institutions in India and abroad, Dr. W. Selvamurthy, Dr. P. Sreekumar, Dr. Jonathan Clark, Dr. Michael Macy, Dr. Afshin Khan, and Dr. Anilia Betty. The topic itself, which has been chosen by the students to undertake a short seven lectures introduction to astrobiology certification program, is unique in its kind. Astrobiology is a branch which tries to explore the possibility of existence of life on other planets or on external outside the solar system. Within the solar system, how does it exist? The universe itself is believed to be about 13 billion years old. The solar system is about 5 billion years old, and the Earth itself is about 4.5 billion years old. It is believed that the life originated on planet Earth around 4 billion years ago. But the life in the human form, or as we see humans today, is only about 2 lakh years old. And some of our seers believe that life actually exists everywhere. There was one saint in India who mentioned, who says life does not exist on sun? When somebody told him that nothing can exist on sun because of such high temperatures, he mentioned, well, life is always formed from the ingredients of the place where you stay. Like our bodies are believed to be made of all ingredients which are available on planet Earth. He said, how do you know that the solar beings who live on the sun, their bodies are not made of fire? How can you discount that? I was left spellbound when I heard this conversation from a very reputed person. So to that extent, to believe that life exists and consciousness exists in the form of mass consciousness, which is available in the planets, in the solar system, in the galaxies, it does exist. That is what is believed as per Hindu scriptures. Coming to astrobiology itself, the art and science and philosophy is so deep and so intriguing. And the limit of human knowledge, we want to break that. We want to go beyond the frontiers of human knowledge to explore what is available and where we can reach. So it's such a wide field which has got unlimited proportions to explore, unlimited knowledge, and some grounds, lot of ground which can be covered. And the quest for knowledge is there in all human beings by nature. So I extend a hearty welcome to all the participants who have volunteered to join this 7 lectures program, which are all on Sundays, and it will give you an excellent insight and motivate you further to take up studies in this field. Soon we will be launching programs with more depth and with greater focus on the subject. So I wish the program a grand success and all the very best. Jai Hind.
Thank you very much, General Sharma sir. I will now request our very dear Dr. Selvamurthy sir to please come forward. Dr. Selvamurthy has vast experience. I've already introduced him to everybody, but
Thank you, Dr. Siddharth.
Yes, sir.
Very good morning and good afternoon, good evening to all the viewers who have joined us from across the globe. And let me convey the greetings and best wishes from our founder president, Dr. Ashok Chauhan, who has built this Amity universe and who is giving a great impetus to research, innovation in all Amity institutions. He wants Amity to contribute to the innovation in a big way at the global level. So today when I see all these brilliant panelists, the resource speakers, and also the guest speakers, I'm delighted to see that you are all going to contribute to this big mission of contributing to society development through research and innovation. I must also compliment Dr. Aseem Chauhan ji, and he is creating the Amity universe in a big way, not only in India, but also across the globe by establishing new universities in various countries. And also, he is very passionate about research and innovation. Wherever he goes to the university, he talks to the scientists, the faculties, and promotes, encourages, motivates, inspires all the faculties and scientists to contribute their best. So thank you very much, Dr. Aseem ji, for this new initiative at one of your campuses, Amity University, Mumbai, where this new center and new activity, Center of Excellence in Astrobiology, you have established. So such a new initiative you have established in many campuses compliment you for this yet another initiative. And General Sharma has been with us almost for a decade now, and he is also looking after Amity University, Madhya Pradesh in Gwalior. And he has served the armed forces for almost 4 decades. And we are fortunate to have him as an academician who has also given the academic input when he was in services, armed forces. And thank you very much, Sharma ji, and also to taking care of this Amity University, Mumbai at this period. My compliments to Dr. Siddharth Pandey. Is a young, brilliant scientist in the field of astrobiology, very passionate and also always with zeal, enthusiasm, bubbling with new initiatives. Compliments to you, Dr. Siddharth, for your connectivity with all these brilliant young the great minds across the globe in the field of space, science and technology, as well as in astrobiology in particular. So I'll continue to do this, and I hope this center, which you are taking as a head of this institution, of the Center of Excellence for Astrobiology, to take newer pinnacles in India and across the globe. And I must also express my gratitude to all the guest speakers, particularly Dr. P. Sreekumar, who is one of our outstanding scientists in India in the field of space science and technology. And his signature is there for in every program of space science and technology. ISRO program, Indian Space Research Organization, not only in technology development, the governance, the lunar mission, the Mars mission, whichever accomplishments you see here today in ISRO, his signature is there during the last 4 decades. And he is now the distinguished Vikram Sarabhai or the Satish Dhawan, the professor over there. And also I thank the president of Mars Society Australia, Dr. Jonathan Clark, and also the research scientists from NASA, Dr. Jennifer Blank, and Dr. also Michael Maxi we will be joining, and also Afshin Khan, and also Dr. Beatty from Mars Society. We express our gratitudes for partnering with us, and we really want to expand, deepen our relationship with you, not only from Amity University, Mumbai, but from other campuses as well. And so we look forward to a very deep engagement with you in the next few decades. And this course, which you have started in astrobiology, is the future. 21st century is going to throw up some great excitement in space science and technology. Astrobiology is going to receive a great focus. So it's very thoughtful that Dr. Siddharth, with your initiative, with the support of Dr. Aseem Chauhan, Amity University, Mumbai, is able to start this new course, which you have started as the first step. And you have also taken many initiatives to make the Mars, the analog center in Ladakh, which is there in 4,000 meters altitude. And that's also, we have to now do a lot of work over there. And if you look at Indian space program, we are very satisfied, and also we are happy that it is emerging as one of the leadership role in across the globe. When you look at the launch vehicle, SLV, ASLV, PSLV, GSLV, and the satellite building, and also technology development, like cryogenic, many technologies, because you are in propulsion, control, guidance, navigation, payload integration, separation, computation, all this tremendous strength India has developed through ISRO, Indian Space Research Organization. And they're also partnering with a large number of academic institutions, including Amity universities. And so this is very great that we have such a great organization, and who have now gone into Mars mission cost effectively, the lunar mission, and now they are looking at Venus and many other planetary, interstellar journey they are looking at. So this program is very important to build the human resource, because we want to build a large number of people will be required in India and across the globe. So that is why Amity, being an academic research driven institutions, we are now giving a focus to develop that well-equipped human resource, the future global citizens who will contribute to space, science and technology, astrobiology and other fields. So this is very important, and the manned space mission is also on the cards, Gaganyaan. Maybe in a couple of years, we will be having that dream realized, that putting a man from India into space, and that's also ISRO mission. And now Amity, we have established not only Amity Space Institute of Space Science and Technology, and in a few campuses, developing, churning out the human resource and experts in the field, future experts. And we have also established a ground station at Dubai, Amity Dubai. We have established a ground station to receive the communications from the existing satellites. Similarly, Amity University, Chhattisgarh, we have established another station of ISRO to receive how does the atmospheric changes, troposphere, stratosphere, those changes, how will it affect the data transmission from satellite to the ground station. So there is another program sponsored by ISRO is with us. We are now developing a CubeSat. We want to put our Amity satellite again from Amity Dubai and Amity University Noida working together. And then the latest one is the first payload, biological payload, is going to come from Amity University Mumbai, from Dr. Siddharth. We are going to put a callus of a plant into the payload, which is going to the space. So such great things are happening, and we have a strong astronomy and astrophysics group looking at the interstellar chemistry and molecular chemistry to look at the distance between the planets. So we are looking at that. When we are looking at that, we are also looking at the biological life in other planets. That's where the astrobiology comes in a big way. And the Mars Analog Station is a very important initiative. And this particular course is a 7-weekly, 1-hour course where all of you are going to contribute, thanks to all the speakers. And we are also, and this comprehensive program, Siddharth has worked out to looking at the habitability of the planets. You know, how do you live there? Then the rise of life, how is the origin of life is another important, building the building blocks of life in space. And then exploring life in our solar systems, particularly solar, because galaxy is huge, universe is huge. And the planetary protection and space policy, very important. Life in Mars, particularly, because we are now reaching close to habitability over there. and research and teaching opportunities for the youngsters who are aspiring to be the astrobiologists. So this is very well thought of. Now, finally, the message is the space science. We want to give a new paradigm. We want to contribute to give a new paradigm to astrobiology. And so the government and private players are also now coming in a big way in our country. ISRO is taking to build not only academic partnership, but industries already they have partnership, but then privatization is also coming in a big way in ISRO. And so I'm sure Dr. P. Sreekumar will mention all this. But let this be a platform to integrate ourselves, network with each other for a sustainable connectivity for decades to come or generations to come. So with this, again, once again, thank all the participants who have joined us in this program, particularly the students and the young budding space scientists and astrobiologists. You have a bright future. So this course is going to be very important. We are going to start undergraduate, postgraduate, doctoral program. So this is just the beginning, a few steps which we are making in that direction. So I'm sure all of you would join us in the programs to come. So with this, I thank you very much for this opportunity to share some thoughts. Thank you, Dr. Siddharth. Thank you, Dr. Aseem ji. And also thank you, General Sharma. Thank you.
Thank you so much, Dr. Selvamurthy, sir, for those very enlightening and inspiring words and the brilliant way in which you have given the complete perspective in which we are setting up this center. I will now take the opportunity to introduce you all to our chief guest who will be giving us the inaugural address. But before that, I actually wanted to convey a word of thanks to ISRO and specifically the Space Science Program Office, who have actually been in close contact over emails and messages with us and helped us kind of identify, what are the requirements that we should really be focusing on within astrobiology. Towards this, we had led the preparation in collaboration with several other astrobiology research groups in India, a small document, which was the Astrobiology Roadmap of India document that has been submitted to the Space Science Program Office. So thank you very much to members, specifically Dr. Sharma Narendranath at ISRO, who has been guiding us in putting this document together. With this, I will now read out a short but illustrious biography of Dr. Sreekumar. He is an astrophysicist by training and currently serves as a distinguished Satish Dhawan professor at ISRO headquarters. He recently superannuated as the director of Space Science Program Office at ISRO. He was also the director of the Indian Institute of Astrophysics in Bangalore, and he currently holds the advisory position at ISRO. After his BSc from University of Kerala and MSc Physics from IIT Bombay, he completed his PhD at University of Hampshire and postdoctoral work on gamma ray observations using the Compton Gamma Ray Observatory spacecraft. After a decade at NASA Goddard Space Flight Center, he returned to work in India for ISRO. Dr. Sreekumar has been instrumental in the efforts towards development of a space science roadmap and has, like Dr. Selvamurthy rightly pointed out, a signature in most of the space science missions that ISRO has embarked upon. He served as a principal investigator on the Chandrayaan-1 mission, India's first mission to the moon, as well as for the AstroSat mission. Dr. Sreekumar has a broad and widening range of interest in research, from gamma ray studies, X-ray studies from cosmic sources, composition of sun's corona, mapping of chemicals on the lunar surface, as well as design of X-ray mirrors for future space use. With this, I warmly welcome Dr. Sreekumar with us, and over to you, sir.
Thank you, Dr. Siddharth. Thank you, Dr. Selvamurthy, as well as the Chancellor and the Vice Chancellor of Amity University. It's a pleasure to be part of this program today. As Dr. Selvamurthy really discussed the broad range of activities both Amity has and what ISRO is having in the near future, and how education institutions and universities like Amity would soon be closer partners in many of these exercises that we are undertaking. Today's program, which is very unique because of the fact that you're discussing an area of research that is really emerging only in India. I mean, until now, we've been actually working quite closely in the space science area, primarily in three broad areas: looking at the sun, looking at and solar system, planetary exploration, and astronomy. And of course, Earth as a system where we have been very much interested in understanding atmospheres, understanding the effect of the sun on Earth's atmosphere, and so on. But the planetary exploration program, which began about a decade ago with our first mission to moon, and currently with the second mission to moon, has matured to a point of actually bringing a lot of interest and enthusiasm in understanding our solar system, its origin and evolution, influence of the sun on planetary bodies, airless as well as those with atmospheres. And as astronomy further expanded in the last 25 years with the discovery of exoplanets, the search for possible evidence of biological molecules in atmospheres of other exoplanets have really become viable given the high resolution spectroscopy capabilities that are emerging. So one of the interesting things we now see is the fact that we are now able to combine the studies that we do of the sun in terms of its short-term behavior when the sun provides interesting events in the form of flares, in the form of coronal mass ejections, solar energetic particle events, and so on, as well as long-term behavior in terms of how it changes its luminosity, and not luminosity, in terms of the variation, in terms of both the radio emission as well as an ultraviolet weak, but however significant changes in the irradiance, and that influences Earth's atmosphere, and we believe that influences other atmospheres of Venus and Mars as well. Now, it is important in the context of these points that I just now mentioned, that is the search for life elsewhere and the discovery of exoplanets naturally leads to the question about maybe life 2.0. And to really address these questions, we really need to start with astrobiology research in our own solar system. And I think that effort, though we have initiated planetary programs, is a little hard to do from an orbital platform. And so that will require actual surface experiments. And these surface experiments are not technically very challenging. We have to really surface, make them move around autonomously, have experiments that can survive the rigor of both launch as well as landing, and the extreme conditions of pressure as well as temperatures and power, which are all critical issues that now, in India, exoplanet studies have largely been with astronomy telescopes, looking at transit methods, looking at radio velocity techniques. But clearly, an important question as we're looking at future programs is a case of a large experiment that has been initiated by the Indian Institute of Space Science and Technology to look for spectroscopic absorption features in the atmospheres of planets going around stars. And so this sort of a discussion on astrobiology is quite appropriate and opportune in the sense that this is a time when we really need to bring our larger science and technology community up to speed with regard to readiness for programs that we are trying to chart out for the future. So I think this initiative of Amity is indeed most interesting and most appropriate. We've had discussions with Dr. Siddharth and others as we are looking at possible roadmaps. However, these are non-trivial because of the fact that we really have to end the emerging scenario of budgetary limitations as well as emerging expansion of many of these areas of other areas of space science as well. It's very important to really chart out those areas that are most appropriate for us to pursue in the near term within the funding limitation that we currently have. And astrobiology certainly has gotten a new spurt of with the fact that India is also now considering a human space program, as Dr. Selvamurthy mentioned, the Gaganyaan program. And naturally, astrobiology and related research becomes very important, both from an application perspective as from a pure science perspective. And so I think this is a very opportune time, and it's very impressive, and we are very glad to see initiatives like this happening at Amity. Pune University has a similar program. And in our view, this would really be a valuable start and a contribution to ISRO in its search for the larger user base, the greater contribution we anticipate coming from both academic institutions, public and private. And I think Amity has taken an important role in pursuing this. So as we begin this program, it is wonderful to see this is a program stretched over a short period of time with experts from around the world, all contributing to this program. Very, very nice thing to do. But I would like to urge you that we slowly build up the level of the program, the quality of the program, such that we actually certainly bring it up to speed with regard to research components, and then work very closely with ISRO and other agencies to really try and do some of these experimentation from space platforms, microgravity to actually low gravity conditions on other systems and so on. Finally, just before closing, I just want to emphasize the fact that, we've been looking at, as we expand our planetary exploration program, we've been looking at Venus as a very important planet, not just because it's habitable necessarily because of the extreme pressures of 100 bar and temperatures of 750 degrees Kelvin is not the best place to be on the surface, but nevertheless it has indeed suitable environments in its atmosphere 60 kilometers above, which one would really love to really bring back a sample of air, which may be very interesting to us, is on the larger question of panspermia, or the question of whether life exists elsewhere in our solar system, and in that search, which is now going on in Mars, a similar approach to really explore such things on Venus is something that we would want to pursue in the long run. So this program, which we have now scheduled originally for 2023, but now given a lot of delays with the current pandemic, we may be shifting to a later launch timeframe, but clearly an important thing, and there are avenues to pursue the astrobiology experiments on it, if not now, at least in future missions. That would be a very important thing that ISRO will look forward to. So let me just close by certainly complimenting Amity University, the higher management that has been very supportive, Dr. Siddharth, who has been actually driving this program quite a bit. And I see that he's also very much in touch with a larger community of colleagues at ISRO Pune and other institutes in the country that are also exploring programs in astrobiology. And we hope to work with this academic community in taking this research component, not the space sciences, this newly emerging component of space sciences, to the goals that we are really laying out for. So thank you, and let me wish the very best. And I hope the students who are going to be enriched from this program, at least some of them would really be part of our long-term program in the country as the years emerge. Thank you.
Thank you very, very much, Dr. Sreekumar. It is actually quite a moving moment for us to reach this stage, to receive these words of wisdom and guidance, from the high offices of ISRO. But also, what we are trying to do here is democratize the entire process of astrobiology, nurturing students, but at the same time proposing research, small research projects that can be conducted in low Earth orbit and within the current capacities of ISRO, and seeing ways in which we can develop the technologies that would be useful one day on Mars or other astrobiology targets. Thank you very much for your very kind words. With this, I would like to bring forward Dr. Aseem Chauhan. So please do join us. You have been the guiding light and vision for us here at Amity. We await to hear more from you, sir.
Thank you so much, Siddharth. It is really wonderful to be here. And at the outset, let me welcome all the students who are online, who have signed up and are participating in this very exciting certificate program, Introduction to Astrobiology. I was thinking, what kind of people are these that are so forward-looking, so visionary to attend a program over 7 days to learn more about this emerging field? So from all over the world, almost 800 students across 53 countries. I think this is remarkable. It is a sign of our times. We live in a time where the problem of our worlds don't seem enough. We are looking beyond to new frontiers, and there is momentum like never before to explore the universe. We see initiatives from amazing agencies like our own ISRO, which is the pride of India. And when I was hearing the words of Dr. Sreekumar, the distinguished Satish Dhawan professor at ISRO, I truly was reminded by the excellence and the achievements of ISRO and what all ISRO has done, not only to complete a number of major initiatives, but also to inspire and motivate others to think about the possibilities that may be beyond normal. So Dr. Sreekumar, we are very grateful to you. This is an amazing program, and any program is only as good as those who are going to teach it and facilitate it. And we really have an incredible set of faculty and supporters for the program. So Dr. Jonathan Clark from the Mars Society Australia. So wonderful to have you online, Dr. Clark. I was reading about you, and your accomplishments and your vision in this area is something that we are very much looking forward to hearing more about today. Dr. Michael Macy, Dr. Afshin Khan, Ms. Analia Beatty, Dr. Jennifer Blank, who looks today as if she's on the moon. Dr. Blank, I love your background. And the many other people, including all colleagues at MSA, Mars Society Australia, Astrobiology at NASA, the Open University, and Blue Marble Space. Really, my gratitude goes out to you, because without the right collaborations, without the right partnerships, we cannot achieve at the maximum potential of what is possible. But when we join hands, when we collaborate, when we share a common dream, then it does sometimes feel that anything is possible and that we can do much more. So my thanks to all of you who have supported Siddharth, who have guided him, helped him. Please continue that. And Dr. Siddharth Pandey, you are an amazing young man. We speak often, and I am always moved by your enthusiasm. Sometimes I tell you, if it does not work, don't worry, you're doing a good job. But for this program, the number of students that have signed up is very encouraging. It's encouraging for the program that we have at the university, for the research initiatives that we are starting, and this small biological experiment that was to go up into space, but because of various current pandemic situations has been delayed, and I'm sure will go up, I think is also a hallmark in innovation and trying to figure out more of what happens to biological systems in different space environments. So I'm looking forward to that launch very soon. Dr. Selvamurthy, I, as always, was very happy to hear your words. You're a great visionary in science and technology. I always say one of the top scientists of the country, and we are so happy that you are working with such zeal to bring Amity to the frontiers of science, technology, research, and innovation. Like we were pioneers in beginning academic endeavors in areas like nanotechnology. We were the first to really begin an academic program in the country, as well as areas like forensic science and cyber law and renewable energy and organic agriculture. Similarly, Dr. Selvamurthy, I think you will agree that the area of astrobiology is also one that we should put a lot of emphasis on, because not only will it help enable activities and programs that relate to space exploration, planetary exploration, but a lot of spin-off technologies, I think, will also be useful in other areas of healthcare science and medicine, which I think could also be very useful. So Siddharth, my congratulations to you, my blessings to you, my gratitude to all the people online. We at Amity are very committed to this particular area. We will look at your continued support. Many of the students online, please be in touch with us beyond the 7-day program. We will look to develop a network of astrobiology around the world of those who are interested and those who are experts, and we look forward to your continued association. And Dr. Sreekumar, one more time, my gratitude to you. Your having come online and given your blessings and words is very encouraging for us, and I will speak to you separately also what more we can do as per you in this area. Thank you very much.
Thank you very, very much, Dr. Aseem Chauhan Sirji. Your wisdom, your guidance has led to all of this happening. None of this would have been possible if we were not given the right vision, direction, and support. So we are always here, and we will make sure that this course is going to be this already is the largest astrobiology class ever. I have confirmed that. So we've already hit a milestone, and we're only going to go upwards and onwards from here. So thank you very much, sir. Thank you for your valuable time. A very, very sincere gratitude to all the dignitaries who have joined us today morning at relatively short notice. We do not take any of this for granted. We think your time is extremely valuable and you're with us throughout. with this, I am now very, very delighted to kick off our first class of astrobiology that will be delivered by Dr. Jonathan Clark. We would really be delighted if the dignitaries can be with us, but please, under no circumstances, feel obliged. You've given us a lot of your valuable time. Dr. Jonathan Clark, I will read out a short bio for you as well, and then I would request you to please come forward and share your screen. So Dr. Jonathan Clark lives in Canberra, Australia, is a senior astrobiologist and Mars geoscientist. He calls himself a Mars general practitioner. Dr. Clark, in fact, has been instrumental in mentoring the establishment of Mars analog research in Ladakh in collaboration with other astrobiologists here in India. And he has supported Amity University since 2016 with the workshops and seminars. And in fact, since August of 2016, again in February 2019 and February 2022 this year, he's been with us instrumental. He's been a guiding force for a lot of us here and truly believes in the potential of astrobiology research and the importance of institutions such as Amity and the work that we are establishing. He was appointed as a visiting faculty in February 2020. Dr. Clark has taken part in 6 Mars analog expeditions to inland Australia, New Zealand, in India, and has conducted 3 rotations at the Mars Desert Research Station. His Martian interests include Martian geology, geomorphology, the terrestrial analogs, astrobiology, and exploration technologies, with an emphasis on habitats, vehicles, and suits. He's also contributed towards mission architectures and several landing site workshops. He currently serves as the president of Mars Society of Australia. He is on the Mars Society International Steering Committee and is the director of science at the Mars Desert Research Station. He had started out life as a paleontologist, doing honors in Silurian paleoecology at the University of Tasmania. He then on became an exploration geologist in South Australia, and he has immense experience working in all different sites and regions in Australia and also in different parts of the world. He has a PhD from Flinders University in Adelaide and brings to us an immense amount of experience from the geology side. And today's topic being, how did the world become habitable? The making of a habitable planet. It gives me immense joy to have him kick off this session. Dr. Clark, you're with us. Over to you.
Okay. Thank you. Thank you very much, Siddharth. It's a great pleasure to be part of this amazing program and to work closely with so many fantastic people at Amity University, in India more generally, and many friends and colleagues from all over the world. It's just a pity because of the current circumstances that more of us can't be together at the same time, at the same place, but that will come. So without further ado, I will share my screen. Here we go. Siddharth, can you confirm with me you can see my screen?
Yes, we can. You just like it in slideshow mode, full screen.
Okay, making a habitable planet. If we're going to be talking about life beyond Earth and looking for life beyond Earth, we really have to start at home. Like charity, astrobiology starts at home. And when we talk about looking for habitability elsewhere, we know we have one example of a habitable planet that is ours. So how did our planet become rather just one planet in a solar system or a planetary system, but one that is actually inhabited by an extraordinary diversity of life and has supported and sustained that life over many billions of years? And what lessons can we draw from that towards searching for life elsewhere in the solar system and indeed the universe? I'll be focusing in this talk on Earth, but the application of these ideas will be relevant to other talks, to other sessions further down the line in other parts of this course. So Carl Sagan, the very famous American astronomer who did a lot for astrobiology, once said, if you want to make an apple pie from scratch, you first have to make a universe. I'm not going to go that far back, but I will start with where planetary systems, including our own, are thought to begin from. And that's in these dark bands that on a very clear night we can see in the Milky Way if it's overhead. And these dark clouds are, if you like, star nurseries. There are where stars and the associated planetary systems are thought to form. In many mythologies about the sky, these dark lanes have a significance. So, for example, in many Australian Aboriginal legends about the sky, people can see things like an emu in the shape of these dark patterns. And you know, we now know that they are, in fact, as important as the bright stars and the bright nebula that we can also see in the night sky, if the conditions are right. Now, the idea is that beginning with these dark clouds, they gradually collapse to form a dense cloud, and eventually, as that collapse continues, these clouds begin rotating and forming a disk. This can be modeled, and as I'll be showing, we can actually see this at various stages in the night sky through our telescopes. In the center part of the disk, the temperatures and pressures become high enough to trigger thermonuclear reactions, and the star is born. One of the properties of this is we see a disk with a protostar in the beginning and jets of material coming out from each pole of the star. And the dark disk that surrounds them is where planets begin to form. First as a disk of dust and other fine grains, then protoplanets, and then eventually, as things stabilize, we end up with a star with different sized planets in various orbits around the central sun. That's the theory, but as I said, we can actually see this. We can see this progression from the dust cloud and grains combining to form larger grains, planetesimals, protoplanets, and eventually planets. Here's a close-up of one of these star nurseries, the Orion Nebula, which is pretty much overhead at certain times of the year for people who live in the tropics. And when we look at the nebula, we see these tiny little dark spots, if we've got a good enough image, like this Hubble image. And when we zoom in on them, we can see that we have this bright central star, a protostar, surrounded by the disk of dark gas. Sometimes we see it more or less face on, sometimes we see it edge on, and in fact the bright star in the center is completely hidden by this rim. These are planetary systems that may be in the process of being formed. Right out there, the sky over our heads. These are some other examples. This sort of hamburger, McDonald's chicken burger structure is again a view of a dust disk and then the bright glow, the protostar coming out on either side. Here's another example of the protostellar disk and the jets that come out. And finally, another image, face on, a central star which has been blanked out so as to not saturate the image. The disk and these dark lanes are thought to be where planets are sweeping up and clearing out the fine particles from those lanes as they are in the process of forming. So the theories that people came up with back in the 18th century are now being confirmed by direct observation. in our lifetime. I mean, these are images that were not possible to obtain, more than perhaps 20 years ago. So it's a tremendously exciting time that we live in, to be able to see planets and planetary systems in the process of forming. So the starting points for the formation of planets are is the interplanetary dust. As they form in the nebula disk surrounding the stars, they form little droplets called chondrules. And here's a section through a meteorite. They're only usually a millimeter or so across, like little beads or little fish eggs, and they form in the hottest part of the solar nebula. They're silicates, they're rock. We also find other little grains, these strange white things, more irregularly shaped, which are what we call calcium-rich inclusions. And they form actually before the solar system, actually in that dust cloud itself. And in the meteorites, we see within these grains, tiny grains, even smaller grains, which are actually older than the solar system itself, things we call pre-solar grains, over 5 billion years old. The rest of the meteorite is about 4.6 billion years old, which we take as the age of the solar system. In between all these little grains, there is a mix of, organic rich material, including amino acids, and other fine particles from the nebula, from the matrix. It's like a cake, if you like, with little bits of fruit and chocolate chips and all the rest, in a matrix of fine flour. This is what we see in a carbonaceous chondrite, which is what we think is the most primitive meteorites. And we know that some asteroids are made up of this material, and some comets are made up of this material as well. And the majority, in fact, of meteorites that fall are of this kind. The majority of meteorites we find, though, are the metal meteorites, which are made of nickel and iron, simply because these carbonaceous chondrites weather very quickly and become indistinguishable from ordinary rocks, whereas a big lump of iron is very visible, and people do find them much more easily. So imagine these small objects, made up of chondrites, which are formed by the melting of interstellar dust grains, then would come together to form larger bodies that we call planetesimals. And we have an example here, a Kuiper belt object well beyond the orbit of Pluto, illustrates how these planetesimals form. So here it is. It looks like a dumbbell that people will lift to exercise themselves, and you can see that within it, it's got various domains. And in this geological sketch map next to it, you can see that they've all been mapped out. And these represent where different objects have sort of come together, and they've retained their identity, but they've been sort of fused together. And we can see another example. This is to the same scale, the comet 67P that a few years ago was visited by the European Rosetta mission. And again, it's got two lobes which are sort of stuck together, but retained their separate physical and chemical identity. Because these are not energetic collisions. These are just two things sort of gradually bumping together under very, very low velocities and staying separate, the planetesimals. But what happens is, over time, these planetesimals get so large that when they join together, they start falling through their gravitational fields, and they pick up enough velocity so when they collide, if they don't fragment, they are actually molten, and they start forming an actual molten body. And we see an example of here with the asteroid Vesta, which from memory is about 400 kilometers across. You can see it start becoming more rounded, There are craters on it formed by smaller impacts. And this is actually the relict of a protoplanet. This is a miniature planet. It's got a crust of basalt, and I'll talk about why that's important later. It's probably got a core, a metallic core, and again, that's something I'll talk about in a moment. But you see, it's still a funny shape. It was originally quite spherical, but various collisions have knocked big bits off it at the top, and especially down at its south pole. So it's no longer really a protoplanet, it's just a relic of one. But it gives us an idea, the sort of small bodies, bigger than planetesimals, smaller than large planets, that would have been common, probably hundreds, if not thousands of these in the early solar system. And these protoplanets would collide to form true planets. Planets such as the Earth, such as Mars, such as Jupiter. And there's an artist's impression here of a planet nice and round, largely molten, being impacted by these bodies. Now, when that happens, when you get a large molten body of rock, it starts separating out. And a very famous German scientist called Goldschmidt, or Swiss scientist called Goldschmidt, made incredible observations about this in the 19th century, studying how mineral ores, particularly copper ores, behaved in a furnace. And he noted that the ores separated out into metals, like copper, like iron, which sink to the bottom, and the lighter elements, like silicon and so on, rise to the top and form what in a furnace we'd call slag. And when you look at a planet, that's exactly what we see. We see in our Earth here a core, which is of nickel iron, and a silicate mantle and crust. And the same was going on in the Earth, throughout the solar system, in the formation of these protoplanets and the larger planets. Some of them, like Vesta, as I showed earlier, have been partially or even in some cases completely disrupted by collision. And so a number of the meteorites that we see are actually from the interior of worlds that have been destroyed. So nickel iron meteorites, pure nickel iron, are from the cores of lost planets, small planets. The stony iron meteorites come from this transition zone between the mantle and the core. And the howardites, which are essentially basalt, like the rocks that you find around Mumbai, come from the mantle, or in fact, perhaps even in some cases, the crusts of these former planets. So when we look at meteorites, we're not only seeing the interiors of what former planets, lost planets, looked like, but we're also getting a clue as to what the interior of our planet is like as well. Now, once that gross structure of the Earth had formed, further processes become possible. One of them is that beneath the outer crust of the Earth, what we call, the crust, let me rephrase that, the outer crust of the Earth is actually rigid, no surprise, it's solid rock. It's about 100 kilometers thick, called the lithosphere. But underneath that, there is a zone about 100 kilometers down, which is partially molten, probably between 10 and 30% molten. And where that is able to escape to the surface, we start forming what are called mid-ocean ridges. And this seafloor spreading, forms collisions where other parts of the crust get sucked down back into the mantle and then partially molten again. And this is what we call plate tectonics. Now, as far as we know, Earth is the only planet in our solar system which has that. And that's probably because the Earth is the largest of the rocky planets. Venus and Mars and some of the other rocky bodies in the solar system, like the Moon, like Mercury, like Io, some of the other asteroids, were all molten at one stage in their lives. And in larger cases like Mars and Venus and Mercury, they probably still have a molten core. But only the Earth was large enough to kick off plate tectonics. And that has an enormous impact on the history of our Earth. Here's another diagram of the plate tectonic process. You can see this at the mid-ocean ridges here. There's a mid-ocean ridge in the Indian Ocean, and that is pushing north. And India is attached to that plate, as is Australia, and that is called, as India is pushed up against the rest of Asia, it forms the Himalayas. There used to be India used to be here, and there used to be a deep trench where the Indian and Australian plate was diving down under the Asian plate. Now that ocean is closed up, and India and Asia have formed this single landmass, but India is still being pushed north against Asia and trying to burrow underneath. And this is what's pushing up the Himalaya ranges. The sort of rocks we get along these mid-ocean ridges are what we call basalt. We also get island volcanoes that form island chains in the ocean, like the Hawaiian chain. And as this plate gets pulled back down or sinks back down into the Earth, it starts melting as well. And in fact, the volatile elements, the water, the carbon dioxide that gets given off from this ocean crust that's being subducted, being pulled down into the Earth, acts as a flux. Anyone who's done soldering is familiar with the idea of a flux, something that you add to another substance that reduces its melting point. People who make glazes and so on do that as well. So water and carbon dioxide coming off this plate going down here act as a flux and cause melting in this upper plate. And that, of course, results in volcanoes. Now, the chemistry of those volcanoes is quite different to the basalts here. These volcanoes here are much richer in silicon and aluminium and calcium, potassium, sodium, and so on. And they form through volcanism and intrusion and erosion and the formation of sediments from that eroded material, what we call the continental crust. Without that process, the Earth would be an ocean planet, maybe a few volcanic islands. But because we have subduction, because we have these formation of secondary volcanoes along the collision zones, we have continental crust, and life as we know it becomes possible. Now, the end result of all this seafloor splitting and subduction is that the continents, which are really like the scum on the surface of a boiling pot of soup or curry, are moved around. This causes continental drift. And here we have a series of paleogeographic maps through time of how continents have wandered around, starting back 650 million years ago, moving forward through time, and forming supercontinents, joining together. Those then break up and start moving. We start hints of the familiar continents here. There's Africa, South America. There's India forming an island, right? This is at the time when the dinosaurs became extinct. And then they all gradually acquire their present position in this map here. But continental drift and plate tectonics is still going on. So in 50 million years' time, the Atlantic will be much wider. India and Europe and Asia may well have joined up with North America to form a supercontinent. Australia is still an island. And then looking 250 billion years in the future, we may well have another supercontinent. So the continents we see today that seem so fixed are moving around like scum on a soup pot or ice floes in the Arctic when you take the long geological time perspective. And you'll hear more about plate tectonics in other talks in this series. But how do we know all this? How do we look back into time and work out how and when and why all of these things happen? This is the Grand Canyon, a very famous part of the world where we can see part of the Earth's history laid down in layers of rocks. Oldest ones at the bottom, youngest ones at the top. And we can use those principles that, you know, you can't lay down an old rock on top of a young rock. We can use these principles of succession, of cross-cutting relationships to work out the sequence of events that form the rocks of the Earth's crust. So, you know, here the oldest rocks are marked in A. They have been cut by a fault here, which has offset them. The rocks have then been intruded by this mass, probably granite, offset by another fault, but that's actually much later, so we'll come back to that. And then the whole thing has been eroded down to bedrock, and flat sediments have been laid down on top. And then D has come in, and then there's been more, there has been the fault here. You can see it's formed a cliff in the landscape. And then lastly, we have this other sediment layer at the very top. It looks complicated, but when you actually just go through it step by step, you know, in any part of the world, you can work out the sequence of events that have made the geology, the rocks of that area. That's what we call lithostratigraphy. Relative time. We don't know how many years, you know, whether it's 10 years or 1,000,000 years or 1,000,000,000 years that separates the events, but we can simply say that A is followed by B and is followed by C. Using radiometric dating, and which involves radioactive isotopes found in rocks and in different minerals, we can work out the actual ages when these rocks were formed. I don't want to get too much into the detail here, but basically radioactive decay works on the hourglass principle. You know, the top of your hourglass or your egg timer is the parent, the sand in there trickles through to the bottom, and we're looking at the ratio between what's in the bottom and what's in the top. You know how long it's been since the process started. Same with radioactive decay. The parent elements decay to the daughter elements at a fixed rate, and by looking at the ratios of these elements in crystals, we can work out how much time has elapsed since those minerals, those crystals, were formed. It's a very simple description of what is actually a very complex process and a very sophisticated analytical technique. So if there are any radiometric dating experts in the audience, please forgive my simplification. And the important thing about both these principles is that they will work anywhere in the universe. So when we go to Mars, we see that rocks are laid down in layers. Right? This is Mount Sharp in Gale Crater, a view taken by the Curiosity rover, and Dr. Jennifer Blank is a part of the team working on that mission. And we know that these rocks down the bottom were laid down before these rocks up the top. And you can see that there are actually a range of different compositions. These are more brownish, these are more bluish. This is a very light color, back to sort of more brownish gray up there. And by driving a rover, or perhaps one day an astronaut walking up these hills, we can work out the history of a sizable chunk of Mars. And these principles not only work on Mars, but anywhere in the solar system, and indeed anywhere in the universe where there are rocks. So let's look at the history of the planet in more detail, particularly what happens on the crust. As I mentioned, the solar system started forming about 4.6 billion years ago, by 4.5 billion years ago, our planet existed, and by a bit over 4 billion years ago, we know from minerals found in very old rocks in Canada and Australia that the Earth had a crust. The earliest continents indeed were forming. There was an atmosphere and there was a hydrosphere. There were lakes and seas on the surface. The atmosphere would have been quite different to what it is now, and these sort of reddish clouds, I think, in this artist's impression are designed to sort of illustrate that. And all sorts of things were going on in that early Earth that we don't see happening now, like these weird lavas that we get in Canada and South Africa and in Australia. They're called komatiites, which are very rich in magnesium oxide, more than 18%. And to get those lavas, you have to have really, really hot magmas erupting out on the surface between 1300 and 1600 degrees. Whereas your average volcano like in Hawaii are erupting out at about 1100 degrees. And these rocks really only occur on Earth before about 2.5 billion years. After that, I think there's only one or maybe two examples known. But before that, they're very common because the early Earth had a much higher gradient of temperatures from inside to outside. Our Earth is getting old and a bit more sedate, and we no longer have these very, very violent lava eruptions. But in this world of very hot lavas, different atmospheres, different water chemistries, we start to find life appearing. The earliest signs of life are things that we call stromatolites. And in fact, if we go back to that artist's impression, actually shows stromatolites growing in the edge of this sea or this lake. Here are modern stromatolites in Shark Bay, and some of us have been there. The Shark Bay is on the west coast of Australia, and here are ancient stromatolites, 3.5 billion years ago, again in Western Australia. They look a bit like Mickey Mouse ears, I think. But these, when we find them in the geological record, show us that there was life around, because these structures are formed by the growth of microbes, usually photosynthetic microbes, cyanobacteria, and some other kinds of microbes as well. We also find them in hot springs. So here's a hot spring up at Puga in Ladakh. Here's another hot spring in New Zealand. There's a champagne pool. It's called champagne. You see little bubbles of carbon dioxide coming up. It's about 98 degrees, not quite boiling. And we've got these strange little bushes here, which are actually mini stromatolites forming around the edges of the pool by microbial growths. We also have all of these sort of reddish brown deposits there, which are arsenic deposits, which wouldn't be very healthy for our sort of life, but the bacteria love it. This material is also running about 2 to 3 grams per ton gold. So it's actually a gold deposit in the process of forming. The microbes were responsible, many of these microbes and stromatolites are, as I said, photosynthetic. And as they released oxygen in the very early Earth, this oxygen would have started building up in the oceans. It would start reacting with various minerals, which would and when those minerals were fully oxidized, that oxygen could start escaping through the water, like the bubbles here off the algae, this algal slime, and building up in the atmosphere. If you look at the oxygen content in the atmosphere over time, we can see that, oops, this goes the other way. We can see that moving from left to right, the oxygen level was fairly low, less than a tenth of it, perhaps about a 20th of an atmosphere. You certainly could breathe that, and then builds up quite rapidly through time with the appearance of more and more life, particularly land life and trees and other vegetation, up to levels that we could breathe. I mean, currently our atmosphere is about 20% oxygen. There have been times when it's been over 30% oxygen. Back in what we call the Carboniferous, when a lot of the world's coal deposits were laid down, not all of them, but particularly in North America and Europe, it was over 30%. And that is actually about as high as it can go. Because when the oxygen goes over 30%, what happens? You get catastrophic fires. You know, we think the fires that are in California now are catastrophic, or in Australia earlier this year, catastrophic. Well, imagine what it's like when there's 35% oxygen in the atmosphere. And when we look at these ancient coal deposits, we can see layers of ash from ancient wildfires. And of course, we have wildfires that removes the oxygen from the atmosphere and brings it back down. So after this period of great activity, oxygen fell down to what we would call more reasonable levels through the time of the dinosaurs to the present. So I talked about the impact of this in the minerals. Ancient rocks are mostly what we call grey stones or grey beds. They're dark grey rocks. They have sulfide minerals called pyrite in them. But when you add oxygen to that environment, we get what we call red beds, because we get oxidized iron. And in fact, many of the world's large iron ore deposits come from the great oxygenation of the Earth's oceans about 2.5 billion years ago. From grey beds and black shales to banded ironstones, and right up to more common red rocks that we find on land today. So in India, for example, many areas we have what people call laterite, which is just essentially an ironstone that's formed through weathering. Many river sands are yellowish or orange because they have oxidized iron in them, because we have oxygen in the atmosphere, which is from life. So life, the presence of life on Earth, has resulted in a complete transformation of the Earth's crust. And so we have this wonderful interplay in a habitable planet. We need certain conditions for a habitable planet. We need plate tectonics to generate land. And once life gets started and it starts producing things like oxygen, that in turn changes the chemistry of the ocean, of the atmosphere, of the land itself, and ultimately the whole crust, because we've had billions of years for this chemically mediated geological processes to be happening. So when we look out at the solar system and further on in the universe, if we want to look for inhabited planets, inhabited at least by microbes, we start looking for signs of these sort of changes, for oxygen in the atmosphere, for organic matter in the rocks, things like coal, coal and black shales and things like that. We look for signs of hematite, where oxygen has reacted with reduced iron in the sediments in the crust to form oxidized minerals. And what is the history of life? Well, the earliest lives we have are cyanobacteria. Bacteria, they don't really have a nucleus, they're just little cells. They can do lots of things. They can deal with very hostile environments. They also have things like they can photosynthesize. But by about 1.5 billion years ago, right, we start feeding what we call eukaryotes. The earliest ones are prokaryotes. The eukaryotes are much more complex cells. They have a nucleus. There are various little organelles, little structures in them that do specialized tasks. They have much more complex structures, as we can see here. And in fact, we are eukaryotes. Every one of our cells has a nucleus. It has complex organelles in it. So we, pardon me, we have a lot in common, even with amoeba and other single-cell animals and plants. Moving forward in time from 1.2 billion years ago, by the time we get to 560 million years ago, we start seeing much larger and more complex multicellular animals, where these eukaryotic cells, pardon me, have come together by a process we don't fully understand to form large complex animals like these Ediacarofauna, which are found in some of the first of these large complex animals to be found. They occur on every continent. They're found in India. They're first recognized in the UK. They're named after a location in Australia, Ediacara Hills. And there are these weird looking animals which often don't have much in the way of modern counterparts. And after that, of course, we started getting more familiar creatures, you know, the trilobites, the early fish, some of them quite bizarre, with the invention of skeletons about 540 million years ago, the Cambrian explosion. And that's something else for another talk. Really, from the point of view of the evolution of life and the diversity of life, we can say the last 540 million years has been, or 560 million years has been the most exciting, because we have all sorts of things. We've got, you know, fossil vertebrates, we've got giant insects, we've got land plants and weird leaves, and all sorts of corals and sponges, all sorts of things developing and appearing and changing the crust. But the billions of, you know, the 2 billion years of life history before that are in fact probably more important, because all of the biochemistry, the cell structure, the microbial pathways, metabolic pathways, pardon me, that allow this diversity to occur, all happened in that earlier history of the Earth. So when we talk about diversity of life today, remember that that is built on an almost invisible foundation of microscopic biochemical and genetic evolution in things that we call rather boring bacteria and algae and so on. And this sort of life, this advanced life too, has had a huge impact on the surface of the planet. So for example, these are Glossopteris leaves, first recognized in India. These leaves define Gondwana land. We find them in South America and Africa, Antarctica, Australia, as well as India. And we show that all these southern continents were once linked together. And leaves like this allow the build-up in the right environment of coal deposits of various types, which were not possible before there were these large, complex land plants. I mentioned the huge oxygen build-up during the Carboniferous. Well, one of the things that allowed, if you've got 35% oxygen, you can, in the atmosphere, you can start getting giant insects. This is a dragonfly with a wingspan of about 1 meter. Yeah, for people who don't like insects, it's perhaps just as well we don't have those around. But I think it would have been rather cool to see bugs of that size. But as much as the increase in diversity of life is important, so is the fact that there are what we call mass extinctions. So through history, there's been the last 560 million years or so, there's been 1, 2, 3, 4, 5 major mass extinction events. And these peaks, there's 2 here which aren't labeled, but they're perhaps earlier ones. But these peaks represent extremely high rates of extinction. So 40%, 50% of extinctions happen during these times, and these periods in between are what we would call normal events. And there are many causes. Some of them we understand. The end Cretaceous was when a large asteroid struck the Earth in what is now Mexico and wiped out much of life on Earth. Some of the others may be related to other astronomical events. People suggested that these may be related to supernova, which produced gamma ray bursts, which irradiated the Earth and killed off a lot of life. Others, like this big one at the end of the Permian, and also at the end of the Triassic, we don't know what caused them. And of course, we are currently now living in what, for many organisms, also a mass extinction event due to human modification of the environment over the last 20,000 to 40,000 years through hunting, through land clearance, through other ways of changing the environment. So some species of animals are no longer, and plants are no longer able to live. But these mass extinctions are really important because after each mass extinction, life restarts. It's a bit like a forest fire. A forest fire obliterates an ecosystem, but it begins again, coming back after that fire, in some cases bigger and better than before. And so the dinosaurs only flourished because of the Permian mass extinction, made it possible for them to develop, and the mammals were able to diversify. You know, mammals were little scurry, furry creatures down here throughout the Triassic and Jurassic Cretaceous, but when the dinosaurs went, they were able to diversify into everything from, you know, rabbits to whales to bats and even human beings. And so when we come back to the most recent past, we start coming into the deep history of humanity. 80 million years ago, we have the first hominids, the first primates that have some affinity with our line. 6 million years ago, the first hominins. 2.5 million years ago, the first members of our genus Homo. 600,000 years ago, archaic humans, Neanderthals, Denisovians, perhaps some other groups as well. And 300,000 years ago, we have anatomically modern humans. You put them in modern clothes, put them in a sari, put them in a suit, and they walk down the road and you wouldn't be able to tell them apart from everybody else. But 80,000 years ago, and these numbers are all subject to change from research, something very interesting happened that we don't understand. People started behaving in modern ways. I don't mean modern as in the last couple of 100 years. They start not only looking like modern humans, but start behaving in ways that we can see as we can see ourselves in. They start burying their dead. They start caring for their injured. I mean, the creatures before here, they may have looked quite human, but if they broke their leg, they would die, just like a wild animal. If you're an antelope or a lion and you break your leg, you either become food or you starve. But well, if when a human breaks our leg, yeah, people care for us. Our legs heal and we're able to resume our place. And when we look at ancient humans from about 80,000 years on, we find that humans are starting to look after each other. We find skeletons of people who lost their arms when they were young adults, but they've lived to their 60s or 70s. We find skeletons of dwarves, people who are congenitally deformed and yet have clearly led long lives. We see the first art, and of course an example there, be it sculpture or painting or intricate beadwork. These are done by people that behave in ways like us. And of course, coming forward in time, you know, the first agriculture, that was 12,000 years ago, 6,500 years ago, the first cities, metallurgy. The agricultural revolution really kicks off about 10,000 BC, industrial revolution a few hundred years ago, and of course 1957, the space age. So that history of humanity, I think, can be summed up by these two footprints. Over 3.6 million years ago in Africa, a naked human footprint by one of our ancestors, and of course in 1969, people on the moon. And this also leads to an understanding of habitability that's going on into the future, that through the technology, through understanding what defines a habitable planet is not simply one like the Earth, but it may also include places like the moon, like Mars, where we could perhaps eventually one day travel to and start building thriving communities on there, new places for humans and animals and plants from Earth to flourish, assuming, of course, they don't have their own life forms there that we need to protect. So that's how we have built our habitable planet. And as we go through this course, I think it's important for us all to start thinking about how we recognize these various features in the planets out there in the solar system, elsewhere in the universe. Okay, that's the end of that. Back to you, Siddharth.
Thank you very much. Please receive our applause from all around the world. Dr. John, you've done an amazing job introducing the class to such a complicated, wide topic, but in such a succinct manner, in a simple manner. And I'm sure that students are taking notes. I'm also delighted to see Dr. Aseem Chauhan and Lieutenant Sharma sir and the others who have stayed with us throughout this lecture. So that's a testament to the amount of curiosity and excitement that we have for this particular field. So thank you very much, John, for that. Any initial comments from our senior dignitaries? We'd be happy to take questions from the students. Yes, sir.
Siddharth, just I want to interject for a moment. Dr. Clark, your presentation was excellent, very informative. And Siddharth, I want to inform you that we also have online listening, and he has been listening throughout the session. Our founder president, Dr. Ashok Chauhan himself, you know how busy he is with
sir.
his work all over the world, but he has been in this session the whole time, despite other meetings also happening. But maybe you can begin the question and answer, and after a little while, we will ask him to also say a few words and share his thoughts. But first, immediately now you can begin, but I wanted to inform you that we have our founder also online, which is so wonderful for all of us.
Thank you very much for letting me know, sir. I hadn't noticed that, and I'm really, really honored to have his audience with us. Okay, so we'll take a few questions. For those of you whose questions are not being tackled, please do not fear. The teaching assistants will make sure that we have all the questions written down, and we'll make sure that all the questions are answered for this session, because it's important for us that all of your voices are heard. The first question is from Neha Potnis. She asks, how does the position of the moon affect the plate tectonics?
Sorry, could you say that again, please, Siddharth?
How does the position of the moon affect the plate tectonics?
That's an interesting question. As the moon orbits the Earth, because of what we call it causes tides, of course we know, and those tides cause the moon to progressively move into a higher orbit. So early in Earth history, the moon was probably a lot closer to Earth than it is now. And people have actually looked at tides cause particular sedimentary patterns in the geological record. And in some places you can actually, you can look at these tidal patterns, and you can look at their frequency, and you can actually work out how many times those tides occurred in a month, and then you can work out how many times the moon was orbiting the Earth in that period, and the moon was actually somewhat closer. So early in Earth history, there was certainly a lot more heating going on inside the Earth from lunar tides. We see this an extreme example elsewhere in the solar system. There is a moon orbiting Jupiter that's called Io, and that's relatively close to Jupiter. The tides are very, very strong, and the flexing of the structure of that moon is so intense that it is largely molten inside. Anyone got a paper clip, you pick up a paper clip and you bend it like this really quickly for 30 seconds and it'll break, and you touch the broken end and it's hot. That's exactly the same thing. So tides by the moon certainly do cause heating, and may be particularly significant in the early Earth in generating that sort of heat that leads to plate tectonics. But there are other sources of heat as well. You think of all those bodies colliding together to make the Earth, they release a lot of heat as well. And that was probably very important early on in the history of the Earth. But there's also radioactive elements inside the Earth itself, potassium, uranium, and thorium. And these decay, releasing heat. And probably most of the heat we get now in the Earth is made up of this radioactive heat that is being generated. But in other solar systems, in other planets, it could be quite different. Io is entirely tidal. Mars doesn't have significant moons, doesn't have significant tides, so it's relying on the primordial heat and also the heat from radioactive decay. Now, Mars used to have plate tectonics, we think, but it's shut down because it is cooled to the point that plate tectonics is no longer possible. Because it's such a small body, it is cooled faster. You know, you get two lumps of metal, put the, one this big, one this big, and put it in the fire till they're both red hot, and you pull them out on your shovel, and the small one will cool down a lot faster than the big one. It's the same with planets. Mars is still probably liquid inside, but nowhere near hot enough to sustain things like plate tectonics. I hope that answers the question.
Thank you. Thank you, John. Here's another question from Nawang Sherpa, who I believe, because I've been communicating with some students joining us from Nepal. He asks, you have spoken to us about the change in the oxygen concentration levels in our atmosphere as the Earth was going through its ages. And you spoke about the importance of measuring that and the role oxygen concentration has played and how evolution of life has taken place. So he asks, how do we know about the change in oxygen concentration in the atmosphere over all these years?
That's a very good question. The effect is quite subtle. The big change is the one I mentioned. So, for example, if there was no oxygen in the Earth's atmosphere, we would expect to find compounds that are what we call reduced. So we'd expect to find iron sulfides, iron 2+ minerals. And we see that. We see pyrite. We see most volcanic rocks have iron 2+ in them, so we know the interior of the Earth is reduced. We start adding oxygen, elements like iron become oxidized. They become iron 3+. And so we see things like hematite, which is an iron 3+ mineral. And we see all of this, and we see these trends increasing over time. So that's how we know that the early Earth had very little or no oxygen, but by the time of 2.5 billion years ago, there was enough oxygen in the oceans to form hematite deposits. And by the time we come to 500 million years ago, there's enough for terrestrial sediments, river sediments, and lake sediments, and shallow water sediments to be predominantly supporting hematite and other oxidized minerals. And you can do calculations to work out what's the maximum and minimum amount of oxygen you need to create that. There are other things like manganese, like arsenic, that you can also look at to try and constrain that. The higher oxygen contents, like during the Carboniferous, and more recently, when the big coal deposits of Europe and America were formed, and to a lesser degree in the Miocene, when again big coal deposits in Australia and Europe and some parts of Asia occurred. It's a little bit harder to measure, but people can calculate the amount of plant material that had to exist to form those coal deposits. And then you can calculate the amount of oxygen they release to the atmosphere, and you have to end up with very, very high amounts of oxygen, 30% or so, as a result of that. Of course, the upper level of that is determined by the fact if you have too much oxygen, then everything burns. And so that sort of controls the maximum, which is about 35%. And of course, we know that from chemistry, we know that from practical experience. If you're doing oxygen therapy in a hospital to people, if you're giving high levels of oxygen, you need special greases, you need special materials in the oxygen supply equipment so they don't spontaneously combust. And so we can calculate the upper level there. But look, it's a little bit of, it's like a jigsaw puzzle, a bit of a piece here, a bit of a piece here, and you join it all together and you hope you end up with a picture of the elephant and not of a giraffe.
Thank you, John. That was great. Another point that I think I should really highlight here, when we go through all of these topics, is that astrobiology is not just understanding the biology. It has so much to do with the atmosphere, how the geology was evolving, how the planets and the moons were evolving. So astrophysics has an important role to play. So it just brings out the complex interdisciplinary nature of the field. Just the fact that the variation of oxygen over these billions of years, how that atmospheric change in fact led to the different ways in which life was evolving. And then you had these extinction events. So I'm going to club a couple of questions and pose it to you. How did we know and how did we measure the percentage or the rate of these mass extinctions? You know, how were they recorded, that there was actually a complete annihilation of a particular species, for example, taking place? What were these records like? And another added question to that is, are we in the beginning of another such mass extinction event? And we're already seeing reports of a lot of different forms of life that are now going extinct. So your comments on that?
Well, some of these extinction events, we've got a pretty good idea of why they happened. I mean, the Cretaceous Tertiary boundary, we've got the smoking gun, or the smoking crater in Mexico. But things are really completely certain in geology, and there may well have been other things going on. So, for example, in the very late Cretaceous, we had these huge volcanic eruptions in India, forming the Deccan Traps. And they were large enough to have a significant impact on things like sulfur compounds in the atmosphere. There would have been a lot of dust, volcanic ash in the atmosphere. And some people think that actually the extinction was already starting as a result of these big volcanic eruptions, and that the asteroid was just the final thing the final straw that broke the camel's back. I mean, with the Permian mass extinction, which is still very mysterious, there were certainly very, very large volcanic eruptions, far bigger than the Deccan Traps, eruptions occurring in Siberia at that time. And perhaps they had an influence. Also, there was big volcanic eruptions associated with large inputs of carbon dioxide into the atmosphere, which of course could cause global warming. There were big sea level changes at the end of the Permian as well. So that one may have been multifactorial. Also, some animals and plants end up in very, very bad positions from an evolutionary point of view. They live in a very small, a very unique environment, or live on one particular type of diet. Because of those evolutionary choices, if you like, even though they don't consciously make them, they become very vulnerable to often very small environmental changes. I mean, the classic example you have in the world today is the panda. I mean, the panda, giant panda living on only basically one or two types of bamboo in a small part of the world, is really painted itself into a corner. And even without humans, it would be very vulnerable to extinction. And it's taken a lot of effort by governments to actually preserve pandas. And there are now more pandas in the world than there have been for many, many decades, which is a good thing. If you like pandas. But there are lots of animals like that. Other animals can survive almost anywhere, like rats. Rats and cockroaches are tremendously successful because they're so adaptable. And they'll be around probably a long time after many other creatures have disappeared. I mean, cockroaches go back to before the Permian mass extinction. They can survive almost anything. So it's very, very variable. One rough thing is very large animals find it more difficult to survive a mass extinction event, which involves a change in climate or environment. So you can imagine taking elephants. Elephants need a huge amount of area to feed, right? If a large fraction if the amount of land available for each elephant decreases, it's harder for the elephants to survive. And this is why they're under pressure in many parts of the world. Something like a rat, it doesn't need a lot of food. It doesn't need a lot of area. And it can survive on almost anything. It doesn't need one type of food. It can live on it can live on scavenging. It can find seeds. It can find insects, and they survive. So it's a very complex process.
And the second part of the question was, are we in the middle of an extinction event?
Yes, in some ways we are. And it's an extinction event that has come in several ways. So around about 40,000 years ago, our ancestors developed two things, it appears. New hunting technologies using new and more efficient tools. And they also seem to have developed the large-scale use of fire. People were using fire well before that, but large-scale use of fire to change vegetation, to hunt game. Some of this was done deliberately, some of it was probably accidental. But because of these two things, more efficient hunting and landscape change, we get mass extinctions in most continents. So in North America, when this technology arrives, in Australia, in South America, on Madagascar, 40,000 years ago for Australia, 50,000 years ago, 20-odd thousand years ago in North and South America, a few hundred years ago in Madagascar. When people arrive with these technologies, within a few thousand years or even a few decades, all the big animals become extinct. Either because they tasted nice or because the environment has changed so much they can no longer survive. The exceptions were the same in Europe as well, about 40, 50,000 years ago. So the other mastodons go, the giant wombats in Australia disappear, the giant birds in Madagascar have gone. And not just the animals that people would have hunted, but also the things that depended on them, like saber-toothed tigers and so on. Two exceptions were Africa and Southern Asia, where we still get these giant animals. We still get rhinoceroses and elephants and giraffes and giant cattle, goor, and so on. And that may be because these are the areas where people have lived the longest, and these animals are able to co-evolve with this technology and survive, living with smarter, more deadly humans. Now, coming into the period of agriculture, 10,000 years ago, a bit less, of course, a massive land clearance. And, we look at ourselves, our own culture, we see, it's terrible what we're doing to the environment, but the most environmentally destructive humans are people with a fire stick in one hand and a spear in the other. And huge extinctions, particularly of plants, but also other animals, happen because of land clearance for agriculture, and that's still happening. And of course, in more recent decades of the population explosion, that has intensified. But it's not all bad. I mean, we have also done tremendous, we recognize this is happening, and we are doing a lot to try and reverse this. And so many vulnerable animals, like the panda, like the African rhino, there are now more pandas in the world, there are more tigers in the world, there are more black rhinos in the world than there were 20 years ago. It's a choice that we have. Our ancestors didn't know better. We have this choice.
Thank you very much, Dr. Chauhan. At this point of time, I am delighted to announce that we are joined with us by our Honorable Founder President, sir, Dr. Ashok K. Chauhan, sir. For those of you, I would like to give a short introduction for him. Dr. Ashok K. Chauhan, sir, is India's leading visionary, industrialist, educationist. He has started the Amity universe, and he leads us and guides us through all of his different emails and messages that we receive every day from him. And I am aware of the short and valuable time he has. So over to you, Dr. Ashok K. Chauhan, sir. We are delighted and honored to have you with us, sir.
I am very pleased, greatly honored, highly satisfied, and have amazing experience today to be with you all. Many instances are remembered for decades, but many are remembered for centuries. Or today, we all are experiencing an event, Amity Center of Excellence for Astrobiology, which will be remembered for millenniums. I compliment Dr. Aseem Chauhan ji, who together with the active initiation of Dr. Siddharth Pandey, in June this year, submitted a concept note to ISRO and DRDO, and they very soon found that this is the area where a lot of research, innovation, and findings need to be done. This is the area which is still not properly and rightly explored. I know about it because few years back, the students of our Amity International School won a competition of NASA, and after clearing all national levels, they were invited by NASA, and there and then itself, they were told to make a concept note for a habitat at Mars. 7 days they were given, and they were to prepare everything, which material, all essentials needed for a habitat at Mars. And the institutions and organizations were called from all over the world. And in the last day, the two teams were declared as which will be going to the final, China and India. And we all will feel proud that the 8-member student team of our Amity International School, Noida, stood globally first. So that way, today's event is of extreme importance for me, because our chairperson, Dr. Amita Chauhan, is far so pleased. These students must have passed out, but I will locate them and we will tell them and will show them today's event. I think this is the area. Following the practice of Amity, we always walk through in the new areas where others have not even thought or considered. I am very glad for the deliberation of Dr. W. Selvamurthy, our very worthy, my brotherly Lieutenant V.K. Sharma, and special compliment to Dr. Siddharth Pandey. I heard from the very beginning, from 9:30 a.m., and the opening remark from Siddharth Pandey. Then I heard the lecture of our ISRO giant, Dr. P. Sreekumar. And also now I'm facing and listening to Dr. Johathan Clark, Dr. Alisa Khadaji, Dr. Misail Mercy, Dr. Afisa Khan, and Dr. Ansela Beaton. These people will be remembered for millenniums. I'm not having any doubt in it, because we are entering in an area where the innovative, brilliant minds are always looking to do something different, something new, something important. The life at universe is such a topic which encompasses many, many areas: physics, chemistry, biology, I would also say anthropology, and all such areas. In the morning, while I was looking it from 9:30, seeing the importance, I immediately sent to 15 of my people from space science, from astronomy and astrophysics, Dr. Suresh Chandra and Dr. Sunita Ratan and Dr. M.S. Prasad. I told them, you should see it. And we will make a chapter. Siddharth Pandey will make a chapter of this grand and unique excellence center at our all university campuses in India, and more specifically at the Global Research Hub of New York, established by Aseem Chauhan ji, to make a big research center at the research hub in 170 acres. I want to show to the whole world that we are going on a path which has never been as yet given the importance which it should be given. Also, I'm very proud to my volunteer teaching assistants. I must name them: Nidhi, Tanvi, Shireen, Anurup, Catherine, and Joel Varghese. I think you people are very wise, very foresighted, that you are so with dedication engaging yourself this. I feel proud that our Dr. Aseem Chauhan ji has fully supported it. And I all thank to all those who have spoken. I heard all lectures. And one very worthy professor was telling, there was an opinion that there can't be any life at sun because of such high temperatures. And this was a learning for me to listen. We thought the idea that why not? If the people are living on planet Earth, they are used to such temperatures, weather, circumstances, the attacks of global warming, climate change. Why he told that saint or monk, which was liked by professor, why should not we believe that at sun, such situations, such temperatures exist where people are used to, their bodies are used to. So I think this gives us a learning in our general life also, that one can not leave anything aside and say, it's not possible to have a habitat at sun or people live there. So I think this is for my all students, a great motivation and inspiration and learning to always think, why not? So I appreciate the worthy professor giving this example, and I bless Dr. Aseem Chauhan. And now we should plan it. Let us register some worthy PhD students. We'll support them. Let's make a center in Dubai, in our all campuses, because this is an area we cannot lose a single day, a single hour. Siddharth, we should move very fast. And also my vice chancellors, they are listening. A large number of faculty members are listening. They will all be the member of the team to make this crusade. My compliment, my congratulations to Dr. Atul Chauhan ji, the brother of Dr. Aseem Chauhan, who is Chancellor and also President of RBF. I would say that Dr. Aseem Chauhan, Dr. Atul Chauhan, and also our chairperson, having a large number of students, brilliant students, I think we are entering a crusade which will be remembered, which will be, example will be given. To my compliment, my blessings, and my appreciation. And this thing, I'm so glad we are having more than 3,500 webinars during this lockdown period. But I think this was one of the most important, because research is my hobby. I eat research, I dream research, I sleep research, I get up research. So when I see this excellent area, you can see that I can work still harder. I'm working 15 hours a day. I can work still harder to see that this center makes an example for all student, research scholar, PhD scholar, postdoc, and people will follow us, learn us. My again compliment to each one of you. Thanks.
Wonderful. Dr. Chauhan, we are so grateful to you. We cannot thank you enough. To all the students and other audience members who may be meeting Founder President Dr. Ashok Chauhan for the first time. People wait for weeks and months to get an appointment and to take even 5 minutes of his time. But the fact that he has come on to today's session on his own, seeing the program and has sat through all of it, Siddharth, I think it's a big compliment to you and to all the experts online that this area is one which has great potential. People say that Founder President Dr. Chauhan can see decades into the future. And I think his words are greatly motivating to us. It will inspire us to do much more work. I think it will galvanize the efforts not only of Amity, but our partners at ISRO and DRDO and many global partners that we have online right now. And we'll put even more emphasis on this area than as we have been doing. So Dr. Chauhan, we're so grateful to you for your time. Thank you so much.
Aseem tell to Dr. Selvamurthy, he should make a brief note to Dr. Sivan, the chairman of ISRO,
yes,
and Satish Reddy,
yes,
and also PSA and NSA about this, because they are very much interested what new things we are doing, and I think this is a thing they will be very glad to read. So Selvamurthy should write on Monday a letter to all of them briefing about this wonderful webinar.
Great. We'll have it done. Thank you so much. Thank you. Yeah, Siddharth, you can continue with the Q&A and as you see fit. Please go ahead, Siddharth.
My immense gratitude to Founder President, sir. I'm still very moved by all the words and the announcements. We have taken due note of all of those things, and we'll be following up and keeping you posted towards that. And also Dr. Aseem Chauhan, sir, for continuing to guide us. What I will do in the interest of time, since we are close to finishing, we will spend maybe 5 more minutes because the questions are not stopping, I'm seeing. But in the interest of everyone being online, perhaps we will take 3 more questions, and then we will stop the recording. We'll end today's show, and then if the students are online, they can continue to ask questions to Dr. Clark. Otherwise, we will take them offline. So quickly, question for Dr. Jonathan Clark. What role has the magnetic field played in the origin and evolution of life on Earth? How does that affect our chances of finding life on Mars?
Right, that's a very good question, and we don't know the answer. I mean, the Earth's magnetic field channels, traps space radiation and channels some of it to the poles, which is why we get the northern and the southern lights. And some people here would have seen those. The atmosphere also, our atmosphere also provides an enormous amount of protection against the atmosphere. In fact, most of the protection against space radiation. So the absence of a magnetic field on Mars today probably isn't a big hindrance particularly to bacterial life that may be living just beneath the surface. So for example, we know the radiation at Gale Crater, where the Curiosity rover is about 254 millisieverts a year. It's a unit of radiation. That's about the same amount of radiation that astronauts get inside the International Space Station. So it's high, but it's not lethal. And in fact, there are places on Earth in Iran, a place called Ramsar, which is a tourist resort, where the background radiation level is about twice that. And there have been studies there that show there are no ill effects in the population, which is a bit surprising because you'd expect that to be the case. There are places in southern India on the coast which have high levels of radiation. And there's a place in Brazil called Gurapari Beach, which is a huge tourist resort. Millions of people go there every year, and it's got 3 times as much radiation as the surface of Mars. And people there look perfectly normal. So high levels of radiation are obviously bad, but low levels are often not as bad as popularly thought. Early Mars, though, is an interesting question because early Mars did have a magnetic field. So early Mars had a magnetic field, early Earth had a magnetic field, and in many respects, pardon me, early Earth and early Mars were very similar, much more similar than they are now. So if a magnetic field is necessary for life to appear, then Mars certainly had it. So we don't know, but an interesting question raises more interesting questions, some of which we can't yet answer.
Thanks, John. Very quickly, next question comes from Devi Souza. Is there any evidence on salty water, even if it is frozen, on Mars, like the oceans on Earth?
Excellent question. Yes. Large areas of Mars are underlain by ice. We can see this. There was a spacecraft back in 2007. Let me just shut this curtain. The sun was getting my eyes. Called Phoenix. It landed up in the Martian Arctic, and it found ice about this far, a few centimeters below the surface. There have been small meteorite craters formed on Mars in the period the spacecraft have been observing the surface, where you can see ice within a meter or so of the surface. The instruments have mapped the amount of hydrogen in the top meter of Mars, and we know that about half of Mars has ice within a meter of the surface, and there's evidence in other places of ice much deeper, 10 meters or 5 meters below the surface. So yes, there's certainly water ice in many, many places. We know from spectral data that there are a range of salts in the soil of Mars. Certainly sulfate salts are very easy to detect. So things like magnesium sulfate salts, calcium sulfate salts, aluminium sulfate salts. Chlorides are a bit harder to detect with remote sensing, but there is some evidence that they are there as well. We know from the Phoenix mission I mentioned earlier, there are these weird salts called perchlorates, which are also present on Mars. And when you add them to ice, they tend to melt the ice down to about minus 60 degrees. Just like if you add table salt to ice, you know, that melts that down. So we know there is salty water on Mars. We do know there's salts in the soil, and also we know there's fresh ice as well. So we've got all sorts of goodies there to study.
Thanks, John. So we will take one last question, John, and request your answer towards that. Before that, I'll point out that the students who have signed up for this course, we will be sending out information on the first assessment task as well. You all have to fill it in the form of a Google form, and it's a requirement for your completion of this course. So details will be on the Google Classroom. So those students who have not yet signed up for it, we'll be having your registrations done as well after this talk. And yes, so bringing to the last question for today, John, what role has electricity played in the rise of life on Earth? Question from Lisa Marie Prasad.
Yeah. There's so many interesting questions coming out of this group.
Sorry for a lot of them being a little outside your area, but
look, I just make it up as I go along, right? All chemistry involves transfer of electrons. So all chemical reactions require, you know, either electrons being added or taken up to form chemical bonds. So all chemistry, and therefore all life, has an electrical component. In more complex animals like ourselves, you know, with nervous systems, the transmission of neural impulses occurs because of movement of ions, particularly potassium ions, you know, backwards and forwards. So not electricity in the sense of wires and so on, but certainly movement of electrons around is essential for life as we understand it. In the early Earth, before life, electrical discharges, lightning in the atmosphere, may have created some of the compounds that are necessary for life to exist. And people have done experiments. So they've got big jars full of the sort of gases that made up the early Earth atmosphere and put sparks discharges through them, and these compounds are formed. So there's a role there as well.
Thank you very much, John. And some of these topics are, of course, outside geology. I'm really delighted the way you're able to actually bring everything together and present it to the audience. So thank you very much for that. With this, I would take the opportunity to close our first session. I'm extremely, extremely moved and delighted by the response I'm receiving, both from the higher leadership as well as from the students, and it gives me more motivation to keep moving on. Thank you very much, Dr. Jonathan Clark, for your time. I would also like to thank Lieutenant General V.K. Sharma, sir, who's been with us throughout the session. Thank you very much for opening the session alongside me and for your guidance. Dr. Aseem Chauhan ji, cannot say enough. Thank you so much for all the guidance, for all the work and the support that you're giving us. And last but not least, of course, our Honorable Founder President, Sir Dr. Ashok Chauhan, who's leading us and guiding us and taking us forward as we establish astrobiology education and research in this country. All the other teaching assistants and class instructors who have been with us, thank you again for all of your time, for joining in across time zones with us. We end this first session with a very, very positive note. And I look forward to interacting with all of you on our next class. So this week, in fact, this weekend, we are having two classes. So the next class is actually not next week, but tomorrow on Sunday, that Dr. Aseem Khan, who is a postdoctoral researcher at Blue Marble Space, situated at NASA JPL. She'll be talking to us on the second part on what goes on behind the making of a habitable planet. And we'll be starting tomorrow at 10 a.m. Indian Standard Time. So all the information is being posted on Google Classroom, and I'll make sure to post the links as well To all the others, we are keeping this because it's an open course. Everyone is free to join into the lecture series and be a part of this. So once again, thank you very much for everyone.